Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about servers data storage, basically what goes on the back end. So let's dive deep into it. So our story starts with SATA. Basically, this puppy was introduced in 2000 as a PATA replacement, aka Parallel Attachment Advanced Technology Attachment. So PATA was like basically if you bought any computer in 1990s to 2000 or second-hand computer from 2000 to 2005, 10 maybe, you would have seen cables like this which were like ludicrously fat for no reason and hard drives which has like giant pajang. So that plug was PATA, Parallel Advanced Technology of Attachment. Now this worked. That's how we got started, and there was a upgraded version of this also, but it was made for enterprise market. So PATA became a very de facto standard. It was used, and if you have seen fast cards, basic compact card in cameras, they were just this miniaturized. Electronically, they were the same thing. So PATA was a very successful thing, but people realized this is way too cumbersome and we needed development. So that development happened in the case of going from P to S, aka from parallel channels to serial channel. So see, that happened, and it got lot of revision. Same way like you have USB and USB goes through revision, SATA also went through revision. So in 2000, when this puppy was introduced, this was 150 megabytes per second. That's a lot. And be mindful, back in those days, there were no hard drives that could even come close to using that speed. Heck, and the capacities of hard drive in 2000 were measured in megabytes, not gigabytes or terabytes. So it was very early days, but people like this was the boom era. So things were exploding way too quickly. So capacity went up, speed went up, and then it was upgraded again in 2004 to 300 ms. That was SATA 2. SATA 2 was gives you 300 ms. Now be mindful, this speed is the upper limit. This is the upper limit of what you can do with mechanical system. Like how can we know this is the upper limit? There are ways like how you can calculate how fast an arm can move. Like you cannot expect it to move 10,000 Gs or 50,000 Gs. There is upper limit to that. And again, if you move it faster, the more your time you have to slow down and all that. So there is a physical limitation. We have increased capacity exponentially, but in terms of throughput, that's still stuck. Meaning, if you have SATA 2, even if you buy a modern 22 terabytes of hard drive, it still has the same speed. And actually 250 mbps read and write speed, that's sequential, meaning if you have to read from one continuous spiral that is going outward almost like CD and DVD, yeah, then you can get that speed. But if it's like random seek and write, yeah, no, you're not gonna get that speed. So SATA 2 was kind of like upper limit, where like they already exceeded what they were made for. However, there was a rumors of flash chips back in the day, so people were like, what if we upgraded again just to have some leeway? So that puppy was in 2009. This was the final revision, meaning after this SATA was like done for. So this final revision turbocharged to 6 Gbps, aka 600 megabytes per second. This is what you have most time. Anytime you are looking at a laptop, unless a laptop, desktop, or whatever have you, if you see a SATA port, 99.99% chance is it's SATA 3. So this was 600 megabytes per second. Now be mindful, this is already 3x faster than what you can realistically get out of these puppies, mechanical disk drives. But flash chip did become a reality, and because of flash chip we can actually utilize this sort of speed, aka 600 megabyte. However, flash chips in the early days, the write speed were super poor. However, most of the time your computer is not writing data to your disks, it's reading from it. Most of the OS file are being read, and thankfully flash chip is awesome when it comes to read speed. It's like it saturated the 600 megabytes per second very quickly, very early days. Like I'm talking like by the time 2015 came around, people could easily buy SATA SSD that could easily saturate the read speed of this puppy. So this was the final system, because we realized this is not going that much further. Flash is coming in and flash will need something better. So SATA was like, pen down was done for it. And as of now, do we still make SATA? Yes, but we do not touch about it. We do not tamper with it. It's just like it's done, it's sorted. It's a what we call a crystallized system at this point in time. You do not have to tamper with it. It's just like done, sorted, move on. So SATA was the step one, so to say, technology. But again, SATA was not designed for heavy load users, but it was like it could have been used for servers. And again, today also, especially for people who are offering backup services, they still use it. It's like it's still low cost alternative. It does work good enough, and if you actually have this thing, more than fast enough. Like be mindful, this is the weak link, not the interface. If you have SATA 2.0, still not a weak link. So that's done, sorted. Then we come to its big daddy, which is SAS. SAS is serial attached SCSI. Now SCSI was the upgraded brother of PATA. PATA also had basically PATA made for consumer use case, and SCSI made for heavy use case. So SCSI also went through the same thing. It also had the same ribbon cable. Then it was like, what if we serialize this puppy? This basically happened after SATA, and serial attached SCSI became a thing in 2004, and this turbocharged interface for server. As of now, when I'm talking to you, this is still the king. So SAS became a thing. Now, SAS from day one was designed in a different mindset, because again, they already learned a lot of lessons from SATA, and this was designed for people who money is not an object. I say uptime is an object. Like, they want uptime. They do not give it amount cost, but they're like, I need uptime. I need heavy use case. So for those sort of people, SAS was built from ground up. So it has basically dual independent link for redundancy, meaning let's say you have a JBOD like this. You have hundreds of disks in a RAID array, and few of disks can die. Your RAID will be like, I do not even give a damn. That's cool, awesome. But here's the deal: how you are reading all of this? You are reading it through a host bus adapter, most likely. So that host bus adapter is the single point of failure. If one of the bus goes, that host bus adapter goes yeet, done. All of these disks which are working perfectly, they are bricked, because again, you cannot communicate with them unless you replace the system. Now, that's how most servers work. But if you are talking about high reliability server, that's not an acceptable option. That's not an acceptable, because again, you have single point failure. To solve that, SAS from day one was utilizing the same interface, basically the same system, but they had a clever idea. It's like, what if we control C, control V it? Meaning you have signal pins of SATA. Again, SATA and SAS is almost the same thing. It's just the electrical voltage and protocol is different. But the core of how many data lines it has, data differential, all of them are same. So they took it the same thing. Okay, we put it here. But what if we control C, control V it and put another pair? This is SATA port B. So if you ever wanted to read data from a SAS hard drive, you can do it by two physically independent paths from the same hard drive. So the idea is you're going to have 5060 hard drive. What is the likelihood of 5060 hard drive poofing itself in one go? 0. What is the likelihood of one bridge interface to poof itself? It does happen. So the idea is you're going to have basically you're going to have SAS hard drives like this. You're going to have a backplane. If designed correctly, you will have a backplane that has two planes. So one plane on the one side, basically, let's say on the front end, it will be connecting directly what we call SAS port A. That's the electronic name of it. SAS port A, all of them are wired through one way, going into one controller. And then there will this signal pin B, port B, aka the other red wire that goes into other side of PCB, completely isolated, like there is a physical isolation, and it will go to second host bus adapter. Likelihood of now both host bus adapter poofing itself is very low. And again, most of the time you will not even put them in same computer. So you will have JBOD, one will go to one head server, one will go to another head server. So that way you have very high uptime. This is built into SAS from day one. It was designed to be very robust. So you can, and again, that's what you see whenever you see a bridge between the SATA power and SATA data. That bridge was specifically put in there. They yeeted that bridge, and in that small area, they put a SATA 2.0, so to say, or backup SATA, so to say. So that's how you can have redundancy. So now, if a hard drive poofs itself, again, RAIDs are designed to handle that. And if a host research after poofs itself, you're still supposed to have a backup path. And this has full duplex, because again, you have to understand, when you're talking about a normal hard drive in a computer system, write happens very rarely. Read happens almost all the time. That's how your OS is being running. So having this simplex option where it's like read, write, that switching is not that big of an issue. Most of the time it's like reading. It's like, but when you're thinking about servers, you gotta write a lot of files. Worst case scenario, a lot of little files, a lot of the time. So that switching, that going tuk, again, it can happen at 600 Mbps, but still adds latency. So latency is not acceptable. So they upgraded the boards and the controller, and now you have full duplex. Benefit, low latency, because that switching from reading mode to writing mode does not happen. It's continuous. And it has a secondary benefit. First, it makes it far more snappy. It's like boom, 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 does that. And because it was built for big people, it was built for multi-device and scalable topology from day one. Meaning it's almost like Ethernet. Ethernet was designed in such a way that it can actually scale up. USB is not meant to. You are not supposed to use USB. One USB will going to one USB hub, then hub is connected to 5-6 computer. It's not meant for that. Try to do it if you want to, but it won't work. While Ethernet, it was built for that. It's like, hey, you take a Ethernet, yeet it into a switch, duplicate it. Heck, you can even do it dumb without any electronics using hubs. You're not supposed to, but you can do it. But that's the whole point. It was designed such a way. SAS is the same thing. It's designed to be scaled. It's designed to be copied to multiple. And then this fully duplex pays off, because again, you can literally have a scenario where hard drive A is being read from, hard drive B is write from. You no longer need to switch. Data is going simultaneously. So that's there. And SAS expander, because again, host bus adapter right now connects one hard drive to one channel. But what if you have exponentially more? What if you have 50,000 hard disks? It's like, dang, how do you connect it? Well, you use SAS expander. And sometimes the host bus adapter does not even know there is expander, because it's not on the host bus adapter, but it's on the backplane. So one backplane would be of course, large version of this. One here, and this itself is I got this. I truncate everything down to, let's say, one SAS channel. And again, that's why back panels of servers are kind of expensive, because again, there are dumb panels, but many times you will find panels that have actual big ass microprocessor. Yeah, generally those are SAS expander. It's designed for that. So it supports large array. 50, 60 hard drive, that's bruh, don't even care about that. 20,000 hard drive, bruh, don't even care about that. It's built for that. So that's there. And it has protocol level error handling. It's almost like it has a pseudo level of ECC, meaning if hard drive poops itself, it actually screams loud enough that controller is like, okay, I got this. This file is put into conflict zone. Again, OS will have to decide what it has to do, if it can trust it or not trust it, or verify it, or whatever have you. But again, there is a communication. It's like something oops happened, exactly like ECC, where your RAM, if something happens, it screams loud enough, then it screams to the kernel. It's like, bro, the last instruction has been corrupted, please rerun it. Again, that's the ideal case scenario, but you get the point. Something bad happened, you should know it before you brick anything. So that can be done. So it's built for robustness. Now, SAS is backward compatible with SATA, meaning you look at Linus Tech Tips. Whenever you see they have giant server, those are SAS system, but they put SATA hard drives. You can do it. It's designed that way. Again, designed in that way. You can just plonk it. You will not get that all the benefits. You will not get any benefits, but you will get the physical compatibility, that at least you can use it. You will get that. Now, because SAS was built for server system and designed to be scaled, they knew very early on, even if one mechanical hard drive does not go very fast, the fact that they could have hundreds of it would read much fatter pipe. So pipe got upgraded after SATA 3, it got SATA 4, basically SAS 4, which is 22.5 Gbps. Now this puppy translates to 2.8 gigabytes per second. Now that's very fast, given the fact that this puppies can barely do 250 Mbps. What about that speed? Well, that speed is not meant for one disk, it's meant for an array. At that point, yeah, this speed is not that fast. So that's why SAS is the backbone. At this point in time, if you just randomly did abracadabra, put me into a server, likelihood of hitting a SAS system is almost absolute. You're gonna hit a SAS system. So that's SAS, Serial Attached SCSI. Then U.2 happened. Now you have to understand, during basically time zone from 2005, people kind of realized that Flash could become a thing. So Flash needed a different kind of way of interaction, because you have to understand, you are always limited by the slowest link. Slowest link was always the basically disk itself, basically the mechanical drive. Basically, if this itself is the weak link, basically the read head going back and forth, that is the weak link, was the point of interface. So nobody bothered with it. But in a SATA SSD, that started to become a weak link. Flash chip was like, bro, we good. Flash chip of 2010, they were like, bro, I got this. But the interface was the weak link. So how can you communicate with PCI, basically PC, the actual CPU core, as fast as possible? You will think RAM. Well, yes, but RAM is meant for processing, as in it puts data there to crunch it. So what is the next best interface? Well, PCI Express. PCI Express is the interface that was designed to communicate to outside world. CPU to outside world, PCI Express. Even the networking and all that, generally it goes through PCI. So PCI goes to a controller converts it into Ethernet or whatever have you, and then it goes on. Again, that's exactly how your South Bridge does. Takes it PCI lane, converts it, and voila, now you have SATA. So somebody's like, what if instead of going through all this hassle, what if we directly take the PCI and dump that puppy into flash chip directly? So they did that. That's what we call M.2. Whenever you see M.2 port in, that's what it is. It's literally PCI lane directly from the CPU cores. So it's very fast. Now again, PCI was not designed for anything. It's designed as an interface. It's like it's a blank. It's like USB. You can plug a USB keyboard into it. You can plug a webcam to it. It's YOLO. Basically, it's an interface. So what protocol should be used? Well, NVMe protocol was built. Now this protocol was from day one built for flash. It was like, imagine a flash that can actually handle that sort of speed. SATA was always limited. It still is limited. Mechanical hard drive is still limited. But what if you did not have that limitation? What would you do? How much queue depth you can handle? How can you handle this and that? All of that is sorted in NVMe. So what is the core difference between this U.2 versus M.2? Now, U.2 was designed for hot swappable, meaning it's a server system, meaning you're supposed to be able to do this sort of thing. Yeet hard drives to it, you're supposed to be able to put hard drives into it. So if you do that with M.2, even if you made a physical caddy that can do that, you will fry the system. Specifically, if the port is active and you dumped it into it, the likelihood of frying your M.2 is absolute. So to solve that, the power rails in U.2 was designed. It's staggered, meaning this power rail, whenever you see power rail, is supposed to be designed the way grounds are connected before anything else. Before energization, ground should be safely connected. So ground pins are generally the tallest, and again it's done in such a way that both, basically the male and female, basically if you have like this and going like this, both will be connecting in such a way that ground will make contact first, then 5 volt, 12 volt and 3.3 volt will be connected. That's the only way to do it safely. So hot swappable was designed because again, NVMe protocol can handle hot swapping. PCI can handle hot swapping. And again, NVMe has wiring built into it. PCI, people do not support it. NVMe built in that way. So power rails for hot swapping, and it has the same hardware as this. Basically the same thing that you plonk on a, basically like this. Same thing. And like, why? Well, here's the deal. Imagine from a service company's point of view, let's say Gigabyte, Asus, or Supermicro, things of that nature. They are making millions of them. You're talking them like, okay, design a completely new thing. It's gonna cost a lot of money. So they're like, what if we can reuse something? They'll always choose to reuse it because again, it saves a lot of money. So, and again, the most likely scenario of a new interface dying is that it's too expensive to adapt. So people will not adapt it, even if it's better. So they're like, okay, what if we use the same physical plastic, so to say? So that same plastic, that's why it looks almost same as a, like, normal mechanical hard drive. It is the same thing. So only the clever part they did is like they filled up all the void place, meaning they had SATA power. They're like, okay, let's not touch it. It's designed for hot swapping. It's designed to carry enough energy. Let's not touch it. Cool. What about SATA power? Let's not touch it. What about SAS port B? Let's not touch it. What are the empty spaces? So you have a lot of empty space above power. Okay, you could, instead of going from one-sided connector, now it's a two-sided connector. And again, technically it's still one-sided data, power is the other side. So you have PCI lanes connecting there, and basically where SAS port B, other side there is PCI lane, and where there is SATA signal, on the other side there is another PCI express. So that's way you can use the same physical port and have no basically fighting in between each other. Now be mindful, it's not backwards compatible. You cannot drop any hardware into it, but it will not supposed to mangle a device. Meaning, let's say you have a caddy like this and somebody joined a SAS hard drive into it. It should not brick it. There should not be any failure. It should be like nothing detected. So the same hardware was used to, it's not compatible, but it's designed in such a way that it should not break physical hardware, physical caddy, all of that should not be reused. And again, it also saves them because they are using the same form factor as 2.5-inch hard drives. So no new caddy design. Basically, server people are very slow to change. They're like, what if we can just Control-C, Control-V this? They Control-C, Control-V this. But it was made for next generation speed and cooling, meaning that's why all the SSD that are made for server grade and U.2, they have such chonkus feeling to it because it's designed for heavy use. It's not designed for your like M.2 where it's like cooling on M.2, it's barely needed. Most of the time your OS is barely putting enough load. But when you're talking about these sort of things, they could be loaded in such a point where the U depth, basically how many requests it has piled up, Q depth, it would be very high. So it will heat up. You need to design in such a way that it can handle the heating. That's why they even have cooling fins or through holes, meaning the actual NAND flash can go through, get fresh air. And PCI generation is now freedom. That was another benefit of jumping from a interface to PCI. Because the moment you jump to PCI, now you are free for the CPU manufacturer. CPU manufacturer is like, bro, PCI 3.0. You're like, go bro, don't worry about it. Like, PCI 4.0, bro, you go with it. Nothing has to change physically. It's like, bro, we good, we sorted. And it's like, what if PCI 5.0, man? It's like, go, bro. Nothing has to, again, signaling strength and all that has to be accounted for, but you don't have to change it. Basically, we went from USB where we went have, oh, now we have extra conductor. That era is gone. In USB C, you no longer have to worry about conductor. Conductor count has been frozen. It's like, we will not add or subtract conductor from it. That's it, done. You just increase the signaling frequency, you increase the this or that, but you do not add conductors to it. Physically is frozen. Same here. Physically, it's frozen. You can have PCI 3.0, PCI 4.0, PCI 5.0, maybe even PCI 6.0, but you do not have to touch it. So it's made for next gen, made for speed, made for cooling, and U.2 is literally working its ass off to save plastic. So people who no longer have to make completely new things. Same CAD design, and even if somebody accidentally put a SAS hardware into it or even SATA hard drive into it, it should not fry or destroy anything. So that's U.2. Then again, if there is U.2, there must be a U.3. There is a U.3. Now, this is just upgraded final form of this. Basically, what if you had one plug like this that can connect to everything? What if you have SATA hard drive? It's like, I got you, fam. What if it has SAS hard drive? It's like, I got you, fam. What if it has U.2? I got you, fam. There is no U.3 hard drive or SSD, so to say. It's an oxymoron to say. You can say it, company will say it's tested for U.3, but like all the hassle happened in the connector, not in the media. That's the whole point of it. It's U.3 is designed such a way that it has tri-mode compatibility. So SATA, SAS, NVMe, and all you have to make sure, like a company that is making the, let's say Dell is making this, what they have to do is make sure the backboard is designed to handle that. Nothing more than that. So if the backplane that is actually going behind, like that is going here, basically on this side, they have to make sure if that can handle it, you can plug a SATA hard drive into it, SAS hard drive into it, or U.2 to it. It will not care. So that's the whole point. And again, host bus adapter, because again, this is just a physical electrical connection. That electrical connection to CPU has to be done by host bus adapter. So as long as host bus adapter can do its job, you're done. Meaning if you have a host bus adapter of SAS, it will only read SAS and SATA. If a host bus adapter is only U.2, you will only read U.2. It will not read SATA, even though physically it can be done. So when people say U.3 SAS controllers, that simply means it's actually tri-mode controller, meaning you can put it behind a back panel that can support all three. And this is the whole holy grail at this point in time. Meaning if you are making a new server as of now and nothing too exact, budget is not infinite, you will go with this. Because it's a great cost saver for hyperscaler. For example, let's say you bought a JBot. You're cool, you're happy with it, everything's awesome. But here's the deal. You're like, hey, you know what? We think it's time to switch to U.2. Okay, cool. Now here's it. In the old days, you throw everything away, buy a new one. Now you can like, what if we just change the back panel, this panel? And again, you will not do it, company will do it, and maybe they can just actually throw it. Or here's a better thing. You buy a U.3 server. It's like, hey, we have a lot of data in SAS hard drive. You do not go through networking. You just pull it out, plonk it here, dump data directly. Like one part, you have flash, which again would be generally larger size. So you plonk it here, let's say 60 terabytes of flash. Plonk it there, you keep putting SAS disk into it, and it just dumps file into the flash chip. Much quicker port times. So all those things are available, meaning if you have a U.3 interface in your server, properly supported host bus adapter, properly built backplanes, you get everything in your choice. You're like, hey, we are putting some cold data. It's just Netflix data. We do not have to worry too much about it. It's like, okay, put SATA hard drive, save money. It's like, no, we need, the data volume is huge. We do not want to pay too much for it, but we do want uptime. Put SAS. It's like, hey, we need like really rapid read and writes. And it's like, it's a very high throughput database set. Put U.2. So it allows flexible asset deployment. And in the same thing, you can do that. You can have like, archive, high availability archive, flash, hyperfast archives, all of that in one hardware. That's U.3. And again, wiring was built in such a way that it could support that. Now they have finally supported it. And what about PCI Express? They should scale up to PCI 5.0. It's tested. You can buy it. Again, unless you are ludicrously rich, you do not look into it. But PCI 3 and PCI 4 is easily available now. So that is U.3, the final interface of as of now. Then we come to the next generation, which is Enterprise Data Center Standard Form Factor, SF, so to say. Now, this is a clean slate product, meaning as far as you can see, you must have seen, like, what if we just tampered with SATA? What if we just tampered with SAS? Everything is just like, what if we do not change much? Now, this is completely different. This is like, okay, let's throw everything away. Let's take all the learnings we got from so many years of experience. What do we need? And we only focus on, flash chips rather than mechanical hard drive. Because again, people have realized early on, it's like mechanical hard drive is not going to go much further. So what do you need for a clean slate product? Meaning there is no backwards compatibility. You do not even think about saving plastic or what if we use the same caddy? No, you just yeet everything. What do you need now? Well, at this point in time, this is a NVMe only system. It's designed for that. They are not even trying to do what if this and this is an NVMe. Go YOLO on it. And it's designed for hyperdensity, aka how much terabytes you can put into it. This puppy can cross 1 petabyte in one U rack. That's like the same size of a router, like an industrial grade router, that's generally 1 U. This puppy is like, I can give you 1 petabyte. Actually, right now, a bit more than that. In one rack, like 1 U. Like you can go bonkers into it. Like this is like, whoa. This sort of density few years ago was undigestible. We are here right now. And again, it's not like a mechanical hard drive. It's like you have the capacity, but the throughput is slow. No. This puppy is like, I got you, fam. I got you, fam. Like this puppy, 1 U can actually serve, Netflix for way too many people. Like you're like, bro, I got this. As long as you have the transcoding capability, I got this, fam. I got this. So this is made for that. It's like made for that hyper density. It's like one rack to rule them all. And it has cooling in mind, because again, that was an issue. SATA does not get that hot, but it is a hot kind of. SAS, yeah, that puppy is hot. And I'm actually shocked how, again, this is why I have this. I was annoyed by 45 drives, horrendous small box that they are making that is so bad that I was like, okay, I'm going to learn and build my own. So the idea is you generally have air coming like this and you have a back panel on this end. That's dumb. That's dumb, because again, you have air flowing through it. Cool, it's taking all the heat away. Now there is a block, PCB block, and that makes PCB cost very high, because now you have to have speed holes there, which is super wasteful. Thankfully, in all the J boards, people have realized that airflow like this is dumb. What if you have airflow like this? So PCB is here, you do not have to have holes in it. Air can go through, can cool all the system. That's why all the J boards that you are seeing, hard drives goes like this. Oh, I have like physical connectors there. Ta-da! Is designed in such a way so air can flow through it, through and through, without any obstruction. No PCB, nothing. Damn. So that's the point of it. Meaning, you see, like they are learning how to cool down. This is like, what if we design it properly from day one? So the idea is the slates, the blade, so to say, will design in such a way that it will have very narrow interface. Damn, I cut myself badly. So that interface will go into a physical contactor that is very small, that is smaller than this system. Why? So air can flow through, meaning each of them can have enough air flowing through them that heating should not be an issue, meaning it can cool itself without too much hassle. So not only you can dump more than 1 petabyte, not only because NVMe protocol can actually handle very high throughputs, and because it's PCI, you can have PCI 5.0, all of that, it can actually cool itself. The connector was designed in such a way that it's 90 degrees from day one, meaning PCB is like this, then you have connector, and connector is smaller than the blade. So it goes like this, air flows through, no obstruction, day one product. And as of now, it has very poor market penetration. Like it has almost zero. The reason for this is it's great, but it's a brand new product. And you can get almost same thing from U.2 SSD. Again, that's why U.2 finally learned that they have to have speed hole. So right now, it has low market demand, but it can become the next default simply because it has so many flexibility. You have super long blades, you have super high heat sink system, meaning, for example, if you are putting something that has lot of read and write, like let's say some sort of RAM module, which is like going lot of read and write, it does gonna generate a lot of heating. They're like, okay, wait, we do this. And again, here's the benefit of this design. Any new technology is generally very inefficient. It's very hot, so to say. Use this. Same interface and everything. Let's say it becomes efficient. Yeet the hard, basically heat sink, put it in a different system. So it's designed in such a way. That's why it has that thing. You may be like, is the point? Like, why don't they like, okay, put it inside that thermal envelope? This is designed in such a way that once they upgrade from PCI 5 to PCI 6.0, it will not be an issue. So they can grab that. And again, it also the bigger one for like really dense data storage, meaning each of these can easily handle 100 terabytes right now. You can just buy it if you have the money. So this is the next generation. So this was my presentation on how the heck server have data interface. So hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst our friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.